Okay, so we've got quantifiers and predicates. Let me do a little bit of a shuffling of papers here. Okay, so we have quantifiers and predicates, and when you put a quantifier and a predicate together, you get a proposition, right? So the predicate by itself is not a proposition, but if it's quantified, then it is. So that's a valid proposition right there, which means we can negate it if we want to. And we had De Morgan's laws for negating ands and ors. We also have De Morgan's laws for negating quantified predicate statements. So it turns out the way that works is when you negate a for all, it becomes there exists. And the negation passes inside the quantifier, the quantified section, right? It kind of passes inside there and gets applied to the predicate. So if it's not the case that for all x p of x, then that means there must exist one x for which it's not the case p of x. It's kind of a long-winded way to say it, but that's what this is saying. And vice versa, if you negate a there exists statement, right? If it's not the case that there exists any x p of x, then it means that for all x's, p of x must be false or not p of x. So that's how those work. Now let's look at an example here. I wrote, not all squares are blue. Well, this is equivalent to saying there's some square that is not blue. And you can see here the all changes to some. That is, this is the first version. This is the all changing to a some. And the not passes from applying to the all, not all, to going inside the predicate and applying to the blue, not blue, right? So there you're seeing the not moving from out here to inside here. That's what's happening. So that's De Morgan's laws for quantifiers. Now, in this video, I just want to kind of bring up a couple other things about quantifiers. One is that in terms of precedence, quantifiers like these take precedent over all other operations, which is why if there's any operations required in the predicate, you'll see me put parentheses around them, because you need to in order to override the operation. So like back here, when I put parentheses around r of x implies h of x, that was required because the quantifier has a higher precedence in the order of operations than this implication does. So we needed to override it with the parentheses. All right. So that's one note I wanted to make about precedence. Another one, I want to issue a bit of a warning. Just be careful with quantifiers. Quantifiers do not always distribute. I'm going to write that down. They sometimes do, but they don't always. And by distribute, what I mean is, like, you can't, well, let me write it. If you have there exists x, and then p of x and q of x, turns out this is not equivalent. Sorry, I missed my x there. This is not equivalent to there exists x p of x and there exists x q of x. Okay? And there we go. Not equivalent. I meant to put a slash through that. All right, so the reason these are not equivalent is because they have different meanings. And we're going to prove that these aren't equivalent by a counterexample. So first of all, I want to explain that over here, the p of x and the q of x both have to be satisfied by the same x. Same x. So there has to be one element of the domain that there exists x, one element of the domain that satisfies p of x and q of x at the same time and makes this predicate true. That's how you satisfy the left side of this thing here. Now the right side over here is different. These, in this case, the x that satisfies p of x and the x that satisfies q of x could be different. This is related to the idea of scope in programming. When you define a variable, variable only really exists within a certain scope, and that's essentially what is happening here. You say there exists x. That x variable only kind of applies, and that quantifier only applies to a certain scope, and that scope ends right here. That scope ends after p of x because we remove the parentheses. So that part there is once you get past this part, we're not talking about the same x any longer. And this x that gets introduced over here, this is in a different scope. So those x's the x's that satisfy those could be different. And now to get a little more explicit and concrete, we can do a proof of this by counterexample. All we need is to choose a domain and then choose meanings for the predicates p and q. and we're going to choose them very carefully so that the left and right sides of this have different truth values, thereby proving that they're not equivalent. So there's lots of different ways to do this, but I'm going to show you one way. One way to do this is to use the domain of integers. Okay, that would be negative whole numbers, positive whole numbers, 0. That's integers. And then we'll use p of x, we'll have that be x equals 1, and we'll have q of x be x equals 2. All right, so the left side is, I'm going to write left-hand side, LHS. Left-hand side here is false, and the reason is that x equals 1 and x equals 2, that statement is false for all integers x. Okay? There's no integer which equals 1 and also equals 2, right? That's contradictory. We know that for integers, these statements can't be true at the same time, right? Right-hand side, on the other hand, is true. And the reason is because on the right-hand side, is there an integer that equals 1? Yes, 1. Is there an integer that equals 2? Yes, 2. So that part is satisfied, that part is satisfied, therefore true and true is true. So that shows, there you go, an example of how parentheses matter when you are working with quantifiers, and you can't split quantifiers over operations like and or. Not always. There actually are some circumstances where you can. So to get a little more nuanced with this, I do want to point out. I should point out that. Sorry. If you write there exists x, p of x or q of x, then that actually is equivalent to the result you get after separating them. And the reason is that the or can be satisfied by one or the other. And so it ends up being equivalent to say either you need to have an x that satisfies p of x, or you need to have an x that satisfies q of x. And that's the same as saying you have an x that satisfies p of x or q of x. So that one happens to be fine, right? That's why it's complicated. If you're interested in this subject, you can think about how it would work with for all. Okay, so I've shown you how there exists can interact with or, either by splitting up and being equivalent, or splitting up and then if it interacts with and, it's not equivalent. Think about the way it would work with for all, and I think you'll be able to figure out. I think you'll be able to figure that out. I think it'd be a good exercise for you to think about that.